I like to look at air mass development. So here's the United States and the heavy dashed line, that's the jet stream. The jet stream is a high altitude, maybe 20,000 feet river of very rapidly moving air, maybe 400 miles an hour. And it's a narrow tube and it snakes around the world. And sometimes it's straight and narrow, and sometimes it's kinked like a fire hose. And when it's kinked like a fire hose, then you get weather. And when it's straight and narrow, you just get pretty much just a lot of flow. So right now it's kinked. And this dotted line, or this dashed line here, is showing the path of the jet. If you look on the null chart today, what you'll see is that over Colorado, and the way to orient, if you look on that chart, you'll see there are little tiny white lines that kind of wiggle across the chart on a landmass. Those are the rivers. And it's a good way to orient to the chart. In the null map today, you'll see there is a very strong little circulation. If you zoom right in on that area, you see there's a clockwise circulation. And that clockwise circulation, that is a high that's in the lee of the mountains. So Denver is in the lee, it's in the downstream side of the flow of air coming from the northwest. When the air goes over the mountains, if there's any kind of release of the pressure, it forms an eddy. So that is an eddy of high pressure air that's forming over Denver. And it's kind of like a big idler gear in the continent. And what that is doing is combining with another high pressure area that's off the coast here and another high pressure area that's over the Gulf of Alaska. High pressure air rotates clockwise. So if I have a high over the Gulf of Mexico rotating clockwise, a high off of Florida coast rotating clockwise, and a high over Denver rotating clockwise, I have a lot of clockwise motion over the southeast of the United States. This whole area is dominated by clockwise high pressure area. You could almost think of that kind of like a mountain in the air. And anything that's coming out of the Pacific and coming down is hitting that mountain of air and will be deflecting off into the northeast. And what's happening there in the northeast, this red line here, these are two little lows that have been generated because of the clockwise motion. They rotate counterclockwise. Those are your weather makers right at the moment, because the jet stream is steering between the highs and the lows. And there's a big low. If you scroll up on the null map, there's a big low over Hudson Bay. So high pressure over the continent and a low over Hudson Bay, those are your major weather makers in the winter. Hudson Bay low is there because of all the ice and snow. Being the Hudson Bay, the open water in the Hudson Bay is warmer than the land. And a warm air rising there creates low pressure. The high pressure off of your southeast coast and on the continent act like a buffer at a low latitude to steer the jet down out of Canada and then across the United States. The jet stream today going through this area is going through a gate that is between Delaware and Pennsylvania, where the mean flow from the continent is steered through that gate. That's your big ticket item. So it just means that the Appalachians kind of right just to the south of you, right where you are, the Alleghenies are starting to rise up again to go up into Maine, into the Monadnocks and all the Green Mountains and stuff up there. They're very high. And to your south, there are the Smokies and things that come up out of the Carolinas. But right between Delaware and Pennsylvania, if you look on them from the air, you'll see that maybe a glacier or something came through and took the tops of the mountains off. Right there, south of Philadelphia, going into Delaware, there's a gap in the mountains, and that gap steers the jet stream into your area all the way from the Pacific coast. That's really a big deal. That's why you get so many prevailing storms coming through, is because whatever is coming in from the west coast is steering through that gap. There's another one in Chattanooga, Tennessee, that's off of North Carolina to the west of North Carolina. And that steers things at a low latitude for you. But right now, that northern gate is producing for you all the strange weather that you're getting. So you're in this slot here of the jet stream. The line with triangles on today's map, that's a cold front. What that's showing you is that the high around Denver is drawing down cold air from Canada into this circulation down below. And that is the circulation down below in the Gulf of Mexico is bringing warm air up, and it's meeting the cold air here and shunting it over into the gate. And you then are getting warm fronts coming down out of whatever is being squeezed up off the continent. And the result for you is snow. So that's the weather map today. And what I'd like to now do is just go back to the chart, the last chart from last week, to take a look at it and see how we can understand what's going on. So here's the equator, here's North America and Africa. So what I described to you with these high pressure areas is that the winds around a high pressure are rotating clockwise. So here you have the Atlantic high rotating clockwise. And in this scenario, that high is pushed a little bit closer into the coast of Florida in the weather map for today. And this high over Hawaii is pushed a little bit to the north. So you get a flow around that high going up into Canada and then coming back down and bumping into the high that's near Florida and then exiting out through your area. This is an extended view of that little narrow map. And these highs here are semi-permanent highs. They're there winter and summer. We're going to look today at how they're positioned in the winter and how they're different from the summer, so you can understand how the weather transitions happen for you in the spring and the fall. So over here is a diagram of the way the air moves in the upper air, the way the currents flow. It's called world wind. So here on the equator, you have maximum solar influence all the time. And what that means is from the equator, there are huge volumes of warm, moist air rising up to maybe 60,000 feet at the equator. They cool off very rapidly at that altitude and then fall back down towards Earth at about 30 degrees north. 30 degrees north on a chart is the latitude of northern Florida. So if you drew a line across the top of the Gulf of Mexico there, that is 30 degrees north. And that area is the mean return for tropical air that's coming off the equator, cooling, and then dropping back towards the surface. Remember last time I talked about Coriolis? Anything going in a straight line in the northern hemisphere veers to the right. So if I have a rifle and I shoot the rifle in a direction at a target that's north of me, after 1,000 yards, that bullet will veer to the right 4 inches. That's a kind of a strange thing, but everything is doing it because of the difference in velocity of the rotation of places on the earth. So anything in a straight line is moving to the right. So I'd like to do a little experiment with you so you can understand where we're going to go. So take your hand, you take your left hand and lay it palm up. And then take your right hand and imagine that there's a line, your right hand is just going straight down towards your palm. So if you do that, you are moving in a line from 60,000 feet down to the surface. We're making a little model of the way the wind would move. So if I imagine on my palm that I have a clock, and I have 12, 3, 6, 9. That's on my palm. And I make a straight line coming down towards my palm. The wind's going to veer to the right. It'll go to 12, and then 3, and then 6 and 9, 12, 3, 6, 9, 12, 3, 6, 9. Looking at that clock, I see that a wind that is moving down is moving according to the clock 12, 3, 6, 9, because it's turning to the right. Now, the strange thing about this is if I keep that 12, 3, 6, 9 going on, and I take my palm away, I'm moving clockwise 12, 3, 6, 9. If I turn that sideways like this, I'm still moving 12, 3, 6, 9. And I have a circular rotation that is the orientation of the jet stream. That's a very powerful river of air, still moving 12, 3, 6, 9. But imagine now that I warm that air and it starts to rise up rather than coming down. I'm still going to keep my hand moving 12, 3, 6, 9, but now I'm going up. But now if I look at the clock, I'm going 12, 9, 6, 3. I'm still moving to the right, but because the air is rising, it now appears to be moving counterclockwise. The clockwise motion of descending air and the counterclockwise motion of rising air is still turning to the right, but they're moving in opposite directions. That's that's what guides the formation of weather patterns on the continent. So when I see a high here on this chart moving clockwise, I know that that's descending air coming down and blowing out. When that happens at the North Pole, the air descends and is moving clockwise. But if you look right here, you see the clockwise air coming out of the pole that's cold is meeting the clockwise air that's coming off the ocean that's warm. You can see that the movements of the two air masses are colliding up here over Hudson Bay and over Alaska. That area where they collide, the cold air turning clockwise from the pole and the warmer air turning clockwise from the oceans, That place where they meet creates a turbulence called the polar front, and that's where storms come from. So that storm pattern there at the polar front is the thing that guides the movement of the jet stream across the continent. And if you learn how to kind of identify it on the null map, or you look at the daily weather map and you can track it, you begin to get a sense of how very small fluctuations of warm and cool and moist and dry will either give you a ton of snow or a little bit. And that even then extends into the summer, whether or not you get thunderstorms for regular rains or whether you have a drought. So here's the idea for the day. This is, we'll do first the summer jet stream, and then we'll do the winter jet stream, and then we can do questions. So in the summer, the sun is high in above the equator, giving direct sunlight to the northern hemisphere. And what happens at that time is there are two major high pressure areas that dominate. And one is off the coast, west coast, that's the Hawaii high. And then one is off the east coast, that's the Atlantic high. And they rotate clockwise. And because it's the summer and there's a lot of warmth in the northern hemisphere, they have a tendency to be pretty much in a steady state, bracketing the continent. And sometimes the high in the Atlantic will shift a little bit to the west and include Florida and the whole Gulf Coast. It gets larger and smaller. But what you can watch, if you watch the null map, this is a fun thing to do. You can watch the highs move east and west in connection to each other. About 10 years ago, I have a friend in England who I've taught my own weather system how to predict weather, and we got a grant to do a study. And what we found in the study was that the position of the high in Hawaii is harmonic to the position of the high off of the west coast of England. And when the high over Hawaii got small, the very same day, the high over the west coast of England got large. And when the high over the west coast of England got small, the high over Hawaii got large. That's a lot of real estate there to be connected. They in meteorological or climate study, they call it a teleconnection. So over thousands and thousands of miles, these air masses are linked to each other on a daily basis. And that's what's interesting to observe about them, is that the whole air mass movement is linked around the whole globe. And if you begin to track that or watch it, your weather eye extends thousands of miles instead of a couple hundreds of miles. And you begin to understand bigger patterns of climate, which leads to things like drought or extreme weather events like you folks are having with snow. If you ask an old timer, hey, when was it snow like this? They say, well, I remember 10 years ago, it was like climate science calls that a decadal influence. So every 10 years or every 20 years, you get a repeat of similar patterns because the jet stream is guided by these fluctuations of these large air masses. And we'll go there down the road. We can look at why that is every 10 years. There are very good reasons why, but they're a little far out for right now. So this is a typical, on the chart here, this is a typical path for the summer jet stream. You have a robust Hawaii high that pushes air up off the Pacific and through a gate in the mountains in Seattle. And that Seattle gate is part of a climate pattern called the Pacific North America pattern. As the Pacific and North America breathe patterns as these semi-permanent highs move east and west and get big and small depending upon the season. Watching these two high pressure areas and how they're operating, the null map is very good for that. You can watch them fluctuate and move east and west linked to each other as if they're part of a chain. And once you know that, instead of being random events, you can watch the atmosphere breathe. That's the beauty of that null chart. So in summer, these highs are strong because there's a lot of warm air coming off the equator that's sinking and expanding the highs off of the two coasts. What that does is it pushes the jet stream further to the north. And when that happens, something called zonal flow, ZONAL, dominates. Zonal flow is a horizontal flow west to east across the continent. So here, the zonal flow from the strong summer jet is going through the gate west here in Seattle, and then going horizontally across the northern tier and exiting through the gate there in Pennsylvania. That's called zonal flow. There's a tendency for any storm activity to just zip right across in a couple days because it doesn't have to go all the way down and then come all the way back up. Zonal flow regimes give you a lot of squall lines and things, very fast moving storms, a lot of thunder type things because it's cold and warm air meeting and then being shunted across the Great Lakes to give you your summer weather pattern. When that happens, there is a semi-permanent low over the Aleutians. That's the balance to the Hawaii high. There's a semi-permanent low over Hudson Bay that's a balance to the Atlantic high. When the highs get big, these lows get pushed north. When the highs get small or shift right and left, the highs can drop down and bring you weather. This is a summer pattern, very rapid movement across the northern states, giving you thunderstorm activity and things like that. The lows in the summer retreat very high up into Canada, and they don't have the power to overcome these very amplified ridges. That's a summer jet stream. So maybe just any questions about that?
Can you say a few words about what makes up a gate? Is that like a topographical, or is it something more than that?
It depends on where it is. So here we have the Rocky Mountains coming up out of with the Scarp in Denver. That's a big block when storms are coming across the Pacific. They have to go over the Sierras and then Basin Range area, and then finally the Rockies out there in Denver, 14,000 feet. So that really puts a big, like a rock in a stream. That pushes the prevailing winds coming in up. Up in Canada, the Canadian Rockies are also 14,000, up to Denali is at 20,000. So up in Alaska, so that's a big block up there. Right south, just off of Vancouver Island and north of Seattle, there's a Puget Sound. And there the Cascades reach a kind of peak, and the Canadian Rockies are not quite as high, and there's a gap there in the mountains that is the mean path of the jet stream off of the whole Pacific. And the reason why is because the winds of the mountains in the south and the mountains in the north are compressed through that gate. They go through Spokane, Washington, and exit in northern Utah. That's like a venturi, and it compresses the air. And if you look on the null map, you'll very often see just to the east of that area, that's where you get really strong winds coming through most of the time. That's like a venturi or an amplifier of wind speed because it's collecting air from the whole Pacific. That's that's a big ticket item right there. That's the Northwest Pacific Gate. Then that
Mm.
air travels across the continent and it doesn't encounter another kind of gate until it gets to the East Coast because it's passed through the Rockies. On the East Coast, you have the Smokies all the way down, going down into Georgia. They get really tall down there. But right, if you look on the null map, where the peak on the East Coast is, that's North Carolina. If you look just to the west of that, you'll see on the null map there's a like a little turbulence. That's when the prevailing wind across the continent is meeting the Smokies, and then you start into the Appalachians, and then you have the Alleghenies, and then the Adirondacks, and then the Greens and the Whites, and all of that going up the coast. There's a gap in Chattanooga, Tennessee for a southern exit, and there's a gap between Delaware and Pennsylvania where something has, I would imagine, a glaciation or something has planed the tops of the ridges of the mountains down. So if you drive through that area, it's like these beautiful little mountain valleys, but the hills are all flat. The top of the hills are all flat. If you look from the air, it looks like somebody took a fillet knife and just filleted the tops of the of a brisket or something there, you know. That's a gap. So when the winds are coming across the continent, they're seeking a gap because the mountains in the south and then the mountains up in Maine, they get tall again up in, so you have these two gaps, Pennsylvania, Delaware, the mountains are low, and in Chattanooga, there's a natural gap down there that steer the jet off of the East Coast. And at present time, you have a very strong flow coming through the Pennsylvania, Delaware gap. Even in Pennsylvania, they say the water gap. There's a gap there in the mountains that steers the jet. Your prevailing winds today are really pouring through that gap. If you look on the null map, you'll see a very strong circulation. So during the summer, you get a horizontal flow coming through those two gates. There's not a lot to change that except for some circumstances. We'll go down the road what changes that. It's a little complex, but for now, we could say this is the mean path of the summer jet, which gives you frontal passages every several days where you get a little thunderstorm or maybe a big thunderstorm, and that's the thing that allows you not to have to irrigate when you're out there. So it's because the summer jet has this kind of steady state. But now we'll look at the jet stream in the winter. So this is the pattern. You still have the two highs here, but in the winter, there is less warmth coming off of the equator moving north because of the way the sun is hitting the earth. So these highs are not receiving so much of a downflow return from the equator. They start to shrink in the winter. And when they shrink in the winter, there is more, instead of it returning at 30 north here, in the Gulf of Mexico, there's much more of a return cycle into the pole. And that activates something called the polar vortex. You probably in the news, you read about the polar vortex because it's like, ooh, the polar vortex. That just means that in the North Pole, there's a lot of cold air that's returning down to the surface and blowing out in a clockwise fashion. Wind up in cold, very cold wind off of the poles blows out. It blows out through two gates for the polar vortex. There's one gate in the Bering Sea. Here's the Aleutians and something called the Kamchatka Peninsula in Siberia. There's a gate here through the Bering Strait where cold polar breakouts shoot through the mountains on both sides and hit the prevailing westerlies and push the jet stream into big long loops. That's called a polar breakout. And there's another one here between Greenland and the maritime provinces that sends cold air down and gives you a breakout here that goes off into Europe. During the winter, because these two semi-permanent highs are low, the high on the continent is also gets locked into the snow here in the desert. So in the winter between the West Coast and Denver, the basin and range area is covered with snow most of the time. And that will attract cold air that's coming down and create a kind of pool of cold air that's actually a huge mountain of cold air that's like a roller gear here over a cold roller gear rotating clockwise. So if I have a jet stream that's coming through the Seattle gate, it usually will bump into that high because that high is locked in. It has like these little Velcro things underneath holding it there. We call them mountains, or holding the cold air in basins. It takes a lot to move that out of the way. The only thing that'll move that high out of the way in the winter is a really strong storm gate that's coming in. And that has to do with the Aleutian low. So it's kind of a crazy thing in world weather that during the winter in the Pacific, the the Gulf of Alaska has warmer water than most of the Pacific. There's a migration of warm water up there every year, starting in the fall. And it gets sequestered up there. And any cold air that's coming out of this breakout here meets that warmer air, and immediately the warm air rising creates a counterclockwise movement. Not only the warm air, but this very strong winds are coming across the mountains here on the Aleutians and on the coast of Alaska. And then there are mountains on the Siberia side here. And as that cold air comes out of the pole, it's kind of like an eddy is created around the mountains to create a counterclockwise movement. So the Aleutian low in the winter is a big storm producer. It's like a mom, and it just keeps spinning off and calving low pressure areas that it sends off, and they'll pinch one off, and then another one forms. It pinches that off, another one forms. It just keeps pushing low pressure cells, little seed cells, into the Gulf of Alaska. And if this Hawaii high is low here and to the west, we get the circulation here that comes in and hits into the Sierras and Cascades, and we get storms. But at this time, this Hawaii high is a little closer to the coast, and it's united to this high, making a kind of block there. So the Aleutian low right now, when it generates something, it goes low and then it goes way high here like this and drops far to the south in the continent. When it drops far to the south, it can come all the way down. It's very cold air that picks up moisture and then gets pushed back up into Canada and then starts to come down again and starts to pick up warm moisture from the Gulf of Mexico as it's trying to get off the continent. It's kind of trapped by the mountains on the East Coast. When that happens, that little cell that's picked up cold and moist comes down, picks up more warm, and makes an end run or goes through the gate in Chattanooga and goes out over the ocean. When it's out over the ocean, this high is circulating, pushing it up the coast. That's to you, that's a nor'easter. And the reason why it's a nor'easter is because it's a low pressure area circulating counterclockwise. And if I look at the counterclockwise motion of a low that's going up over the coast, it's pulling water off the ocean. But when it gets to your area, the wind is from the northeast. The actual storm is to your southeast, but the weather is from the northeast. And the reason why it brings so much snow is because it was cold air that came off the continent and moved out over the ocean where the cold air is picking up moisture and then it comes in and hits the mountains and gets lifted again and you get dumped on from the ocean. So it's a northeast, it's called a nor'easter, but it's actually coming from your south. It's kind of a, yeah, I'll run through that again. My high over the Rockies is blocking. A low is generated in the Gulf of Alaska that has cold and maybe picks up a little moisture, but the high here is sending it way up through Vancouver and the Canadian Rockies up into Canada, where it picks up a lot of cold air. But because this high in the winter is very, very stable because of the cold air in the basin and range area, it's called basin and range, it tends to push the jet way up into Canada during the winter. So my jet stream goes way up into Canada and gets very cold, and then it meets a low here that gets large and small over Hudson Bay that is also pretty permanent because all the land is cold, but the water is warm. So that's a permanent feature counterclockwise. This is a permanent feature clockwise in the winter. So the jet loops way up and then comes down.
When it goes up like that, does it increase in mass?
Well, that's a really good question because the mass of it is made of water. And the water has a relationship to temperature. When the temperature is high, the water is in the form of vapor. When it gets cool, the water shifts from vapor to actual precipitation. That play between the vapor phase and the precipitation phase is what all the computers are programmed to try to figure out. It's called dry adiabatic lapse rate. That's what it's called, DALR. And the DALR determines whether you get a powder snow or a wet snow. It determines whether you get tendency for storms to move rapidly with a little bit of precipitation or storms to be very slow that drop a lot of precipitation. That lapse rate makes it possible for storms coming across the continent to wreak havoc on the East Coast. That's basically what I'm trying to explain to you is why your weather is so variable from year to year. It has a lot to do with how these highs and lows are shifting east to west. So right now, you're having a jet stream that is going up into Canada. And when you get a nor'easter, it goes all the way down and comes all the way up, and you get a lot of snow. Right now, you see, and it's usually pretty heavy snow. So right now, this is going into the north, but the ridge here over Denver is pretty strong. So it's pushing, instead of dropping down, it's pushing across like this through the gate. So if you got snow out of this, it would probably be more like a powder kind of snow and kind of light, not a lot of heavy dumping. Wouldn't be a blizzard. It'd just be a snowstorm. And that's because it's not picking up a lot of moisture off the ocean. So these patterns are semi-permanent because they're kind of there all the time, but they change depending upon a lot of different conditions, and they change at about a 4.5, 10, and 20-year rhythm. So you could look at your weather data 4.5 years ago and start to see patterns that were maybe similar, but certainly 9.5 years, you could see you probably were having very similar weather 9.5 years ago. Because there's a pattern having to do even deeper levels of this, having to do with the way that eclipses are operating. And we'll go there as we go along, but that's a little far out right now. These are just basic, standard climatological features. I hope this makes sense for you. If you look on that null map just for a couple minutes in the day, you'll start to see this high here now on the null map will come up as a very dark area. And the reason why it's dark is in the center of a high, the winds are very calm because the null map is showing you surface winds, not upper air, surface. So this will be very dark here, but then if you zoom in, you'll see that there are lines around it that are being circulated in a clockwise fashion. Right now in the null map, there's a very strong continental flow right here because the ridge is, if you look at it, you'll see it's buffering, and then a very strong flow coming off of the East Coast here, pushing out into the Gulf Stream of the Atlantic, making a huge storm center south of Greenland. That's going to be a big ticket item for Europe in a couple of days. That's going to be a really big problematic storm because there's so much air pouring off of the continent, cold air pouring off the continent across the warm water of the jet stream. That's going to be, and we could look in the paper at storms in England and Scotland in 3 or 4 days and see that they're going to be hurting there for a little bit. So that's what I mean about looking upstream and downstream. If you learn how to read this a little bit, the catastrophic kind of weather or very intense weather makes a lot more sense. It's not just moving randomly. There are very clear images of why it's doing what it's doing.